Hi, everyone. Thank you for joining today's seminar. This will be our last seminar, and it's my great pleasure to be able to introduce today's seminar speaker, Professor Jariwala from UPenn. Professor Jariwala is an associate professor and the Peter and Susanne Armstrong Distinguished Scholar in the Electrical and Systems Engineering, as well as Material Science and Engineering at UPenn. He completed his PhD in Material Science and Engineering at Northwestern University and was a postdoctoral fellow at Caltech before starting at UPenn. His group's research interest is broad, and it lies at the intersection of new material, surface science, and solid-state devices for computing, optoelectronics, and energy harvesting applications, in addition to the development of correlated and functional imaging techniques. His research has been widely recognized with a tremendous number of awards. I'm just going to name a few of them here. So these awards include the Optica Adolf Lum Medal, the Bell Labs Prize, the AVS Peter Mark Memorial Award, IEEE Photonics Society Young Investigator Award, IEEE Nanotechnology Council Young Investigator Award, the SBIE Early Career Achievement Award, and the Sloan Fellowship. Professor Jariwala serves as the Associate Editor for ACS Nano Letters and has been appointed as a distinguished lecturer for the IEEE Nanotechnology Council for 2025. So it's a pleasure to have him here today with us. The floor is yours. I just remind everyone in the room, if you want to ask questions, feel free to raise your hand directly ask. We do have audience over Zoom. Please type your questions and I'll help moderate. Please help me welcome our speaker.
Okay, great. All right, thank you, Farnaz, for the very kind introduction, and thank you all for making it here. It's a great pleasure to speak here for the MIT.nano seminar series. I realize that my pointer is not going to work in this peculiarly reflective screen, so I'm just going to use my hands to point to various things on the slides, okay? Let me get started by thanking the people who actually do the work. I often say at the beginning of my talk, I'm a professional panhandler who goes and seeks for resources to run my research, and actually it's the students and postdocs who end up doing all the important work in the lab. So definitely none of the work would be possible without them. Certainly we have been very fortunate to be funded by a wide number of funding agencies, both in the government as well as industries and some private foundations. And finally, all the work that I'm presenting, especially the III-Nitride work, has been done in collaboration with Professor Troy Olson and Eric Stack, who have been my partners in crime in this amazing new area of research. Troy Olson used to work in nitride piezoelectrics for a long time, and so together with him, we were able to switch to nitride ferroelectrics. So with that, let me introduce the broad divisions in the research group. The research group is divided into three major sections. The first one is what I'm going to be focusing most of my talk on today, which is nanoelectronics. Here we look at both the logic and memory devices, which means transistors as well as memristors of some sort that can do either logic functions or data storage functions. Certainly, I won't be able to talk much about logic today. It'll be focused on the memory aspect. Then the other part of the research, which actually is very quite closely related to Farnaz, Professor Tisdale, Professor Bulowich's research, is in the area of novel excitonic materials for optoelectronic applications. And that's another very active area of research. Certainly in 1 hour, I cannot cover both of them. So I'll be focusing my efforts on a portion of this area. And finally, we also synthesize new materials via both MOCVD, sputter coating, as well as some solution phase chemistry too. Again, much of that, I mean, the sputtering part I will introduce in a slide, but won't be able to cover most of it today. Hopefully another seminar, another venue, I'll be able to cover that. Okay. So let me harp in on the focus of today's talk. It's all on III-Nitride ferroelectrics. I'll first, given this is a broad seminar talk, I'm hoping there's audience from various departments at various stages of their career. So some amount of broad introduction would be helpful on what are nitride ferroelectrics, why are they interesting, why are they useful, why could they potentially open up some very interesting applications, including commercialization of the technology. Then I'll focus the second part of the work on ferroelectric memory devices that you can make out of them, namely both for in terms of transistors as ferroelectric FET devices, as well as ferroelectric memristors or you could say ferroelectric diode memory devices, right? And then finally, if time permits, and I may just rush across this large portion if I don't have enough time, is why these nitride ferroelectrics are kind of a match made in heaven for data storage in extreme environments. Okay, so let me start with the big picture question, which is grand challenges in modern classical computing. I know a lot of you would be probably working on quantum computing and have heard a lot about quantum computing. Certainly, quantum is very exciting, very interesting. There is a lot of interest in it, probably a lot of hype in it, right? But I should say that classical computing is a moving frontier. It is something that is evolving every day or every month, right? And new challenges come up. And there are sort of two major or central challenges to classical computing. One of them is power consumption. And this graph was created by the SRC, Semiconductor Research Corporation, which shows you how ICT applications, which is information and communications technologies, are consuming energy on a global scale year after year. And you can see that the computing and communication graphs are quite nonlinear compared to the global energy production, which is rather linear on a log scale, or rather straight line on a log scale, which means the global energy production does not increase by more than 5 or 6% a year unless MIT or some other university works out fusion, right? In which case that graph's slope can increase much more rapidly, or we figure out a way to do computing and communication much more energy efficiently. We are going to face some kind of crisis, and not too far away from now, right? We're around here, 2025. By mid-2030s, data centers or energy for AI compute is going to consume a vast fraction of electricity or energy that humankind produces. There is a second problem, which is sort of connected with the first problem, which is current big data compute or AI compute, which is largely driven by crunching vast amounts of data, searching, pattern matching, inferences, right, is quite inefficient, both in terms of time and in terms of energy. And the central bottleneck for it is popularly known as the memory bottleneck. What is this bottleneck? Let me try and explain. Now, this is a graph taken from a startup company's website, but this is also widely available on several government websites now. There are two graphs over here. One is a rather nonlinear looking exponentially increasing graph. That is the graph telling you how many number of parameters each of these, the progressing number of AI models that are coming out, right? These parameters run into the trillions now. For example, GPT-4 is up there. I'm sure many of you are using it to do your homeworks or writing papers, right? It's in the few trillions, right? That's the number of parameters GPT-4 uses. You can call it the weights, right, in the model. This line over here, which is somewhat less sloped, linear looking, that's the amount of memory available to today's best AI processors. This is the DRAM memory, which basically stores the weights, and then the model is running through these weights. And so you can see that the amount of memory available versus the amount of parameters required, there is a large exponential gap between them, and it's only going to increase, right? So this is the quote-unquote memory wall that slows down or makes AI computing more energy hungry, more energy inefficient, and somehow this needs to get solved. So the bottom line is there is latency between the logic and memory units, and that's a major bottleneck known as the von Neumann bottleneck, which leads to increased power consumption, and sort of these problems are in some sense connected. Why is this important? Certainly we as a society, especially as academics, do care about energy, right? And what we are going to face is this kind of a scenario based on the previous slide's graph, which is if you look at our whole society together, today we are doing a certain amount of computes in terms of joules per year, right? And these green graph tells you how many compute operations you are doing, right? And these compute operations are measured in what is known as ZIPS, which is zeta input, output, or operations per second. Zeta means 10 to the power 21. Certainly, we have MIT as 10 to the power -9, but it's 10 to the power plus 21, right? And so, again, this graph was created by the SRC pre-ChatGPT revolution, but this is only going to accelerate further. And if we continue to go across this trajectory as a society, we will have to saturate our computing needs at some point to about 1,000 ZIPS. I mean, these numbers vary depending on who you ask, what type of people are doing estimates of this. But we do need electricity or energy for other things. Even if you drive all electric cars, you need some energy to charge them, heating up, running these lights, right? So there has to be some delta between the green graph and the world's energy production. And so this essentially is going to lead to computing saturation. So the only way forward for us is either you increase the slope of the yellow graph, which means bringing along fusion or some other transformative new energy source in the next 5 to 10 years seems highly unlikely, or reduce the energy required for computing per bit or per bit of compute, right? And then you can get in the blue trajectory and have a much larger amount of compute possible. Now, as a society, we have been doing this for a long time, okay? If you look at this graph, again, taken from a very nice perspective by Marinara and Agarwal a few years ago, the y-axis is, again, exponential scale showing you the energy efficiency of compute per bit or per bit operation, right? If you look at the topmost point, that's ENIAC that was invented in my department, the first general purpose computer made out of vacuum tubes, right? So when ENIAC used to be turned on, the whole of electricity of University City area of Philadelphia used to be shut down just to power ENIAC, right? Comprised of vacuum tubes. It used to consume about a few hundred joules per bit of energy. Look what happens on the y-axis. There is a break in the y-axis before the next point, which is IBM PC. There is a transformative change in the hardware technology. You move from vacuum tubes to semiconductors. There's a 6 orders of magnitude jump in the computing efficiency right there, right? You went from vacuum tubes to semiconductors. By that time, integrated circuits were realized, which went to the IBM PC. It was pretty clear to people, the game is simple now, scale down. Moore's law, Dennard scaling takes over. That helps you out until mid-2005s right here. And for those of you who are in the computer architecture field, you would know this is around the time when Intel's processors, which are dual core, quad core, and all these started coming out around 2005. Why? Because at a single core level, computing was not, the speed was not increasing any further, efficiencies were not getting gained. So therefore, the so-called architectural revolution started around mid-2005 right here. That is going on all the way until today. Apparently, this is also the time when GPUs were introduced, and so-called GPU era started, and GPUs progressively started becoming more important, and CPUs started becoming less and less important. And today, we know how fortunes of Intel versus NVIDIA has flipped, right? And so that's because GPUs have become way more relevant than CPUs, right? But here we are today, somewhere close to 2025. If you look at the compute energy per bit of NVIDIA's best processors, they are in the couple hundred femtojoules per bit, very close to the thermodynamic limits that silicon CMOS presents, right? This is physics. You can't cheat with physics. You can cheat with architecture. You can cheat with engineering and scaling. It's very hard to cheat with physics. This is where we need a transformative new technology to continue to increase our energy efficiency for compute. What is that? We don't know. Some people say photonics. Some people say quantum. All kinds of names are being thrown around, right? All kinds of technologies are being thrown around. We don't know. Maybe it's completely new state variable. Maybe it's completely new physics. Or it could be the same technology, but integration of new materials and devices, right? This is sort of the shortest term solution, is to introduce in new materials and devices to enhance architectures even further. And this is where our community mostly sits, which is designing new materials, devices, and systems that maximize bit operations per watt of power while sticking to this electronics platform, right? And that is why a bunch of people in our community, including Farnaz and many others at MIT, are focusing on new materials to do computing much more efficiently. And not just computing, but also other variants of computing, like generating light, modulating light, which is the photonic aspects that involves communication and so on. So in that sense, certainly novel materials, low-dimensional materials, both optical and electronic materials, have sort of dominated the research community. Here is a long list of those materials, or a long chart of many of those materials. My group ends up working on all of them, by the way, right? Certainly, I cannot talk about all of them today. I'm going to focus on these two over here. Among them, I'm going to focus further on the III-Nitrides, okay? So let's try and get into it a little bit further and try to understand where this problem can be solved by III-Nitride ferroelectric materials. So as I already mentioned or alluded to in the few previous slides, dense integration of memory and logic is necessary. If you look at the current computer architecture, including the latest and greatest chips out there, they are like a strip mall parking lot, right? Like you would see when you go to Chicago or, well, Illinois, or in the middle of nowhere in the country, right? They're all spread out, right? So the processor cores and the memory units are all separated out. They are all connected in 2 dimensions. And the rate of data transfer is limited by this 2-dimensional connectivity or bandwidth, right? And so this basically creates a traffic jam when you're trying to run models with extremely large number of parameters requiring extremely large amounts of memory, right? So the solution to this is something that has been well known for a long time, which is going 3D, basically New York style architecture, right? Tall skyscrapers with bottom floors being the computer microprocessor, right? The logic, and all the above floors being memory units that store the data. And now, instead of 1 or 2 or 3 elevators, you have 10,000 elevators going across those buildings, right? That will lead to data transfer rates, or the bandwidth of data transfer could be extremely fast. You're moving data from millimeter or centimeter scales to micron scales when you're building 3D. So there's a giant gain, and there is a giant gain also in the bandwidth of access of data that you can get. Right, so this has been the holy grail, or in some sense, from the computer architecture's perspective, going 3D. And to go 3D, you need something that is back-end of line compatible memory. Once you make the silicon secret sauce, you want to make memory on top of the silicon secret sauce, which means it has to be compatible with silicon process, and therefore it's called back-end of line compatible. Silicon is called front-end of line. And so back-end of line compatibility means it should be able to sustain certain number of elements that are allowed in silicon foundry, temperatures, reaction gases, all those things should be compatible with silicon processing, right? For example, the temperature limitation is about 400 degrees Celsius. You cannot move more than that. Otherwise, the dopants and other layers inside the silicon process get disrupted, and all your process is a waste, okay? So in this space, there has been an intense competition for memory for the past 30 years, and several technologies have been tried. Many at MIT have also made huge strides in many of these technologies, right? There are 4 major ones. I don't want to debate about all of them. I'll pull up a chart later that may rile up a few people, but we'll talk about that at that time. First, one is RAM, or standard memristors. Second is phase change RAM that Intel tried to commercialize and then wrote off their entire business for a few billions. That was a couple years ago. And then there is MTJ, which is still under commercialization, has not made it into mainstream, right? Magnetic tunnel junctions, or ferromagnet based, so ferro-based technologies. And the last one is ferroelectric, right? If you were to ask me personally, one of the 2 ferro technologies will ultimately win out for various reasons. But I would like to highlight why this is a very challenging problem and why it has taken so long to solve, because memory is a much more brutal market than transistors. For memory, the device performance requirements are extremely stringent. You need very low energy, you need very high density, you need them to be extremely fast, you need to be back-end of line process compatible, and you need them to be extremely reliable. Getting all of these things together in a single technology is extremely difficult. This is why no single technology is one together to date. We hope the technology that I'm going to show you potentially has a chance. There are other competing technologies too, but we're definitely betting on our horse. All right, so let's go into ferroelectric technology and why that is so special. It's not a new technology. Ferroelectrics have been known for a long time. The year 2022 marked 100 years of ferroelectricity. Does anybody know who came up with the word ferroelectric? Does everybody know Erwin Schrödinger? Well, he also came up with the word ferroelectric, but he's known for better things than ferroelectric, right? OK, so he came up with the word. So it's a very old word, very old technology. If you've taken Tokyo Transit, you have used the Tokyo Transit cards. They have a chip inside them that actually contains this memory. So perovskite-based ferroelectrics have already been commercialized. They have a problem with scaling, and they also have chemical compatibility problems. They have lead and bismuth. No silicon foundry wants lead and bismuth in them. Also, they cannot be scaled below 50 nanometers in thickness. They self-depolarize and cease to exist as a ferroelectric. Hafnia, Hafnia-based ferroelectrics, another very exciting class of ferroelectrics. Professor Chima, he's not here right now, but I met him earlier. He's been working on them for a while. They have their own problems too, but they have made it quite far in terms of process control and engineering. They were first discovered in 2006. They are slowly trying to make their way into commercialization. They have other problems, which I can talk about later. And then the last ones, which were only realized as a ferroelectric in 2019, these are the nitride ones. They also have their problems. I'm going to try and show you one by one. We have tried to solve or address most of these problems. OK, so what are these ferroelectrics? Now, these are the same structure as gallium nitride or aluminum nitride. It's a Woodside crystal structure. I'm sure any of you from material science departments or people who work with 3-5 materials, you know about the Woodside crystal structure. You can have either a metal polar or a nitrogen polar state, and that basically stores your up or down polarization of this ferroelectric, and therefore your memory 0 or memory 1, right? So it's very simple. As you're switching the ferroelectric from one polar state to other polar state, all the unit cells move all the atoms move half a unit cells up or half a unit cell down. That's it. And the polarization flips. There are no weird pathways or circling around or anything like that involved, which is true in many other ferroelectrics. Compare the hysteresis loops of these ferroelectrics, aluminum, scandium, nitride. first reported by this group in Fraunhofer Institute and Kiel University in Germany. They're almost ideal square-shaped hysteresis loops as compared to lead zirconium titanate, which is very, very small and tiny in the center as compared to it. But the even more exciting part over here is that the remnant polarization, the amount of charge remaining behind in the ferroelectric is extremely large, of the order of 100 microcoulombs per centimeter square or more. This is so much charge that it can lead to some very dramatic performance enhancements in devices, which you'll see as we move forward. By the way, I should mention over here that this is not some exotic material that was just discovered and it'll have a hard time making its way into commercialization. If you all bought a phone after 2020 or 2021, it's likely in your phone as a piezoelectric BAW filter. So the piezoelectric properties of these materials are already commercialized. Now we are trying to commercialize or discover and report the memory storage or data storage properties of this material. Okay? All right, there are many other advantages. I'll go over them very briefly. We have summarized them on this review article. It's a full class of materials. It's not just an isolated material. The aluminum scandium variant is the most mature, successful one. But there is gallium scandium nitride, zinc magnesium oxide, aluminum boron nitride, aluminum yttrium nitride. The list goes on, right? The key features are the following: large coercive fields, large remnant polarizations. Okay. A second very important property: extremely high stability. You cook this thing up to 1,000 degrees Celsius, keep it for days, bring it back down, the data just stays there. Nothing happens to it. Very rare property, not there in most systems. Right? Extremely important for data storage, information storage in high temperature environments, which I'll talk about towards the end if time permits. Finally, it's also one of those materials which has low dielectric constants combined with the ferroelectricity. That means it's to switch it, the energy required is very low. Last couple points I'll mention: it's a uniphasic material. It only exists in one phase, the Wurtzite phase. Normally, in many other ferroelectrics, you have to compete for phases, which is a problem if you want phase homogeneity over entire wafers. And finally, this material is fully back-end of line compatible. You can deposit these films even at 100 degrees Celsius or even at lower temperatures. The Japanese do it at a room temperature, and they turn out to be perfectly ferroelectric. Okay, so it's also done in a process that is quite friendly and used in industry at scale. We do sputtering of this. Certainly, most other groups also do sputtering, but there are also groups that do MBE, MOCVD of this material, even PLD, pulse laser deposition. I'm hearing reports that atomic layer deposition, or ALD, also works, but we'll see. We haven't seen any conclusive reports here yet. But you can deposit it on full 6-inch wafers. We are poor. We can only afford 6-inch tools, so that's the maximum we can grow up to. But there are companies out there that can do this up to 12 inches, right? And so certainly it's scalable outside the university into actual commercial fabs. Okay. The substrates are usually silicon wafers, sapphire wafers, or silicon carbide wafers, whatever wafer you want. The typical preferred substrate is hexagonal crystal plane. Symmetry is preferred, right? We can do films all the way from centimeter by centimeter to full 6-inch wafers, thicknesses from 5 to 2 microns, temperature range of diffusion between 250 to 500 C, depending on the application. Okay, let me go to the first application of the memory device application of these ferroelectric, which is the ferroelectric field effect transistors. Ferroelectrics as a whole have several device applications. A few of them are shown on the screen over here. I won't be able to go through all of them. This is the classic or conventional FE-RAM memory where you have a ferroelectric capacitor connected to a transistor which senses out the current. This is the ferroelectric field effect transistor where the ferroelectric is direct contact with the semiconductor. Ferroelectric is the gate dielectric in direct contact with the semiconductor. Okay, so that moves me to the second part of the talk. So naturally, if you have a transistor, you need a semiconductor channel. This semiconductor channel in our case is 2D materials. And so the question is, why do I care about it over here? The short answer is half of my group works on 2D materials, other half works on aluminum scandium nitride, so combine the two. Well, that's a perfectly wrong answer. That's not how you're supposed to do research, right? There's actually a deep fundamental reason behind picking these two materials as a combination. But let me highlight the advantages of 2D semiconductors. They are potentially back-end of line compatible. You can transfer them or directly grow them on wafer. They can be extremely high quality at very small thicknesses without the need for epitaxy. This is important. Most 3-5 semiconductors are going to need epitaxy. 2D materials do not need epitaxy. This is going to be their main advantage for future integration for commercialization purposes. And the very thin channel of the 2D materials can mean they can support, or you can induce electrostatically large carrier density, which will lead to very low resistances and therefore very high speeds of operation. If you want to take my perspective, unfiltered perspective on the future of 2D semiconductors, we've wrote a perspective article last year on it. We have written it quite critically in both domains, electronics and photonics. You're welcome to take a look at it. Again, I won't have time to go into the details of why 2D, why not 2D in today's talk. We've also written an article on 2D ferroelectrics and ferroelectric semiconductors. A large number of 2D materials have now found to be ferroelectrics. There is a lot of excitement over there, too. I encourage you to see that article. But the argument of why you want to combine aluminum scandium nitride with 2D channels actually came from a paper more than 22, 23 years ago now, written in IEEE EDL. My students don't like to read these journals. They're very low impact factor, they tell me, right? They only want to read Nature and Science, which are mostly fake. But nonetheless, there are gems hidden in these journals, right? And there was a gem written by T.P. Ma about 22 years ago as to why is the non-volatile FE-FET still elusive. It was a purely theory paper. And he basically outlined, with the help of two equations, that if you want to have data preservation inside an FE-FET, you want a low depolarization field, EDP, and you also want a low rate of loss of polarization, which is dP over dt. And to achieve that, you want a high CIS, which is interfacial state capacitance with the semiconductor. And in the ferroelectric, you want large EC and low K. This means you need thin semiconductor channels. And large EC and low K means they are possible with aluminum scandium nitride. In 2002, neither 2D materials were known, nor AlScan was known. In 2020, when we started this research, we immediately identified this combination and went to DARPA. And they took the bet on a very unlikely research such as this, and they funded us, right? And so that sort of started a lot of this stuff. OK, so we went ahead and started making these devices. The early devices were on quite thick materials, such as 100 nanometers of thick aluminum scandium nitride, grown on platinum, which is also sputtered. You can do platinum, you can do aluminum, we can do various other metallic electrodes. They have to be hexagonal phase. Platinum is templated 111. Therefore, woodsite aluminum scandium nitride grows very well on it. This is approximately 100 nanometers thick. We made transistor devices. They had very nice hysteresis loops, almost square-shaped. I should mention these hysteresis loops now are in current and voltage, not polarization and electric field. So you can actually sense them out and program them in circuits. It's really important. OK. Again, these devices look extremely well in terms of switching numerous times, storing data for a very long time. I'm only showing you 10 to the power 5 seconds over here, but we have gone through months now without loss of data, which is extremely good. If you normalize the memory window of these devices to other competing technologies, including that of hafnia and silicon, this sort of wins out in many respects. This is, again, old data. This has only become better over time. Certainly, 2D materials are now scalable. Professor Palacios and various others have grown these materials over wafer scales. They have also grown it at BOL-compatible temperatures, so all this makes it very appealing. Certainly, we have not grown them at BOL-compatible temperatures, but Professor Redwing, who is 2-3 hours drive away from us at Penn State, she grows these films over sapphire wafers. We can transfer whole wafers of this material onto wafers of aluminum scandium nitride and make hundreds and hundreds of devices, and then you can get some very nice performing transistors. These transistors can be reduced in their operating voltages. For instance, if you reduce the thickness of the aluminum scandium nitride, the operating voltage reduces. If you increase the scandium concentration, the coercive field reduces, and therefore the operating voltage also reduces. You can see a comparison of a aluminum scandium nitride FE-FET with compared to a silicon oxide with similar thicknesses. Silicon oxide FE-FET has about a few hundred times lower current, even at larger sweep range of gate voltage. So this highly nonlinear behavior comes from the ferroelectricity of the aluminum scandium nitride. Again, just to show, you can make nanoscale devices, really shrink down the channel lengths. You don't really see any effect in the transistor performance. You can measure hundreds of these devices. They can have very large memory window and on-state conductivity, very important for fast operation. You can partially polarize these ferroelectrics. And if you can partially polarize the ferroelectrics, you can partially change the conductance of the semiconducting channel, which means you can potentiate it and depress it just like an artificial neuron. Again, people who are interested in using hardware implementations of neurons for neuromorphic computing, this is a great avenue, or people who just want to use these devices as analog memory, this would be a great approach to that. We have published several more works on FET devices, or field effect transistor devices, out of aluminum scandium nitride and 2D materials. I don't have the time to go over all of them, but I'll just mention them. We have made them using tungsten diselenide, wherein we can also get very high on-state current density. Again, the ferroelectric introduces very large carrier density, which means the on-state conductance or current density can be very large. Similarly, the channel resistance can drop significantly if you have a very highly doped channel. And we've also demonstrated the negative capacitance effect. This was work actually that Sri Krishna co-led, who's now in Palacio's group. And so we have demonstrated all the major phenomena that you would get using by pairing ferroelectrics with a novel semiconductor. So with that, I'm going to switch gears and move to a different type of ferroelectric memory device, namely the ferroelectric diode memory device. Okay, this is very similar to a memristor device. This does not have 3 terminals now. This has only 2 terminals. This does not need a semiconductor anymore. So the ferroelectric diode device is nothing but a sandwich of aluminum scandium nitride, or it could be any other ferroelectric, in between 2 metallic electrodes with an interfacial layer which is a non-ferroelectric insulator. It could be an oxide insulator, it could be another nitride, what have you. Right? Now, the way this device works is, depending on the polarization of the ferroelectric, the conductance or the leakage through the ferroelectric is widely different by orders of magnitude. Right? And so this gives it the memoristive or resistive memory phenomenon. Right? Not only that, it is also highly nonlinear and highly asymmetric, therefore the diode-like behavior. This is very advantageous for various reasons. One, it becomes a voltage switch device rather than a current switch device. A lot of the RAM and phase change RAM are current switch devices. You are actually passing a certain amount of current, basically joule heating the thing until the filament forms or breaks. Right? You don't need that over here. So this is much less power consuming as compared to RAM and PC RAM. PC RAM is already sort of dying out slowly. RAM is still used in some circles, but scaling it is going to become a big challenge. Okay, let's see. Okay, this ferrodiode effect, or FED effect as we call it, has been shown in other ferroelectrics too. For example, in hafnia, people have shown it a few years ago. Professor Chima just showed me he was working on similar effects in his hafnia films, as well as these 2D ferroelectrics like copper, indium phosphorus sulfide have shown the same effect as well. So it's widely known now. It's not something obscure or absurd or one-off thing that we are seeing. Compared to the standard resistive memory, again, like phase change RAM or RAM, which are this quite symmetric and linear devices, this is highly nonlinear and highly asymmetric. This means that unlike any of these devices which would require a pairing or selector transistor in the underlying silicon hardware, you don't quite need it over here. This reduces the hardware complexity quite a bit and the hardware overhead you need in the underlying silicon, making it way more energy efficient in terms of in-memory compute or compute-in-memory operations. Just to give you a very simple illustration or example over there, you could build an architecture known as ternary content addressable memory, or TCAM. Right? This is a typical architecture used in searches. Like if you want to do search and pattern matching over large bodies of data, you would do this. If you wanted to do it in silicon CMOS, you would need 2 SRAM cells, which means 16 transistors. If you want to do it with standard resistive memory devices, you'll need two memristors, which are those resistive elements that you see, and 2 transistors. But if you want to do it in ferrodiodes, you'll just need 2 ferroelectric diodes. And depending on how you polarize them, you can get charge, discharge, or don't care states over here. Again, I'm happy to go over the details of this later on. You can also refer to the paper if you're interested. So then if you project that into the search delay versus cell area required, you can see that it wins out over all the other memory technologies that you want to use for search and pattern matching applications. Certainly, the energy consumption also drops by a significant amount. This concept won the Bell Labs Prize a couple of years ago, which prompted us to think further into commercializing this whole area. Naturally, you can shrink down the dimensions of the ferroelectric quite a bit. When we first started this field, a lot of people would not believe that you can scale down the ferroelectrics to such small thicknesses and maintain ferroelectricity. The oxide community was hell-bent on believing themselves that this material was refused to remain as a ferroelectric when you scaled it down to below 10 nanometers in thickness. Turns out even at 5 nanometers, these diodes work pretty well. I have data showing this material itself can switch at about 2 volts or so as well. I can share that later. You can also have program into multiple memory states, like about 32 states over here. Very linearly, you can program it and deprogram it. Again, very useful for synaptic behavior in neuromorphic computing. Here are some other data showing that when the field started several years ago, people were making a micron-thick devices, which are not even on this scale. But then in like 5 short years, give or add another year, thanks to COVID, you can shrink it down to, we have managed to shrink down the device thicknesses to about 5 nanometers. And the important thing is, even at 5 nanometers in thickness, the remnant polarization of this material stays quite close to the bulk remnant polarization. This is an important parameter showing that you can truly scale the material and preserve its ferroelectricity at the same levels as bulk. There are many important challenges to solve over there, namely reducing the coercive field at small voltages, which we'll talk about. OK, I want to mention a couple more things. This has now been scaled up. You can definitely make crossbar arrays instead of individual devices. We are making full 2 to 10 kilobyte chips. Here's a 4-inch wafer of 10 kilobyte chips. We are dicing them out, wire bonding and packaging them, and sending them to companies for testing. I'll tell you why they would want such low memory sort of density chips in a few slides. But even in the bad clean room that we have, which all university clean rooms are bad, but ours is way worse than yours, right? Yours is much newer too and much better maintained. So anyways, you can see that even in the few hundred devices that we measured, the yield is about 99.4% at 10 micron device sizes, right? Done using the mask aligner photolithography. And then the distribution of switching voltage is what is important to note. If you try to compare resistive RAM or phase change RAM memory, this distribution is much wide, of the order of a couple of volts. We're talking about switching voltage distribution under 100 millivolt or so, which means excellent uniformity of the material over large area wafers, right? And again, the on-off ratio has more distribution, but that is because of the interfacial layer made using ALD, which is not ideal. The next question we get is, can you really scale these devices down to extremely small nanometric dimensions and maintain lateral dimensions and maintain their memristor performance? Turns out, yes. This graph shows you that 50 micron and 50 nanometer devices have an area scaling of about 1 million times. But then if you take that area scaling and convert it into current densities, actually all the graphs overlap on top of each other. This shows you it's a hyper-uniform material from the micron scale down to just a few tens of nanometers. This would be unthinkable in case of RRAM, for example, where you're forming filament and the filament formation becomes more stochastic the smaller dimensions you go to. OK? All right. The last thing that people ding us upon all the time is you're never going to be able to make a ferroelectric switch billions and billions of times, because that has always been the problem in ferroelectrics. In the oxide ferroelectrics, people have overcome it after 8-10 years of work. But here, there is a huge advantage that that we were not exploiting so far, which is the large polarization. If the total polarization is 100 microcoulomb per square meter square, you don't have to switch the full polarization from top to bottom. You have to only switch a fraction of it. If you switch only a fraction of this polarization, you get your memory readout quite well. And if you do so, if you partially polarize the aluminum scandium nitride, you can actually reach cycling endurances exceeding 1 billion. Right? We have data showing, in some devices, we have data showing exceeding 10 billion as well. And this is still being done at device dimensions of about 10 microns or so. These are the smallest device dimensions. We hope that when we start doing endurance measurements on even smaller dimensions, like 100 nanometer, 50 nanometer diameter devices, we should be able to break the sort of thresholds that are required for commercialization, which is typically around 10 to the 11, 10 to the 12. OK, so what's the memory landscape look like? Memory is a very tight landscape. There are many parameters on which people evaluate memory. Again, I've listed many of this. This table can rile up a lot of people because of the numbers. I've tried to go with very conservative numbers over here. Some people tell I'm giving too much leeway to other technologies over here, given what they offer commercially. But you can see that the Alscan ferrodiodes is kind of beating all of the technologies in most metrics. Right? The endurance one is still something we are working on. We expect that to even cross 10 to the 10, 10 to the 11 in the coming years. HBM DRAM is the volatile memory currently used in most high-end GPUs, or NVIDIA's chip, if you will. If you want to compare ferroelectric diode memory to commercially available RRAM from TSMC or Skywater, again, on most metrics, we have beaten these commercially available technologies, with the exception of voltage. And this is something that we are trying to solve now. We are hoping, with the help of Intel and others, we'll be able to address that too in a year and a half of time, and will be ready for prime time commercialization at that time. But even without that, there is a particular application where this material could have could use this memory technology right now, and that is in extreme environment computing. Why? Because as you can see from this chart, this is one of the few thin film ferroelectrics, probably the only one available, that is extremely stable at elevated temperatures. Now, why do you need to store data in those temperatures? There is a whole field of electronics in extreme environments. We wrote a review article on that recently. And there are several material challenges over there in various domains: packaging, interconnects, logic, gate dielectrics, memory, et cetera. The memory problem is particularly severe because there has never been a commercially available non-volatile memory that can operate more than 250 C. Today, if you go in the market and ask someone, I want a non-volatile memory to store data at upwards of 250 degrees Celsius, they'll tell you it's not possible. The best available is a flash memory by Texas Instruments or some other small companies that also needs to be refreshed every 100 milliseconds at 250 degrees Celsius. So there is no way to reliably store data today at elevated temperatures. And there are many applications for that. I don't need to go into it, but many defense and nuclear power applications, but also in oil and gas exploration, automotive, industrial electronics, and so on, certainly space applications. Now, if you want to think about just logic transistors, they have been quite well achieved or solved at elevated temperatures. Like silicon carbide technology is pretty mature over there. NASA has worked on it for several years, right? And they have 800 degrees Celsius transistors working quite well. This is how some of NASA's processors that they wanted to use on Venus look like. They don't have too many transistors, as you can see. About 1,000 to 10,000 transistors. This is a few years old, but about 1,000 to 10,000 transistors is what they have on silicon carbide dies. And most of the transistors are used as SRAM volatile memory, leaving an extremely few number of transistors to do actually compute. So in this case, if you had a non-volatile memory device where you stored the data and forgot about it and only just went and accessed it when you needed it, the amount of computing power could grow by leaps and bounds at elevated temperatures. And the prime such application to begin with would be jet engines and downhole drilling exploration in oil and gas exploration. And so we have now tested ferroelectric diodes, the same concept that I showed you a few slides ago. It works extremely well up to 600 degrees Celsius. I have unpublished data that is going up to 800 degrees Celsius. You can see the resistive memory effect sustained quite well up to 600 degrees Celsius. The on-off ratio drops a bit, but we have now used interfacial layer engineering to also bump this up to about 50 or so at 800 degrees Celsius. You can see very clear ferroelectric switching. In fact, ferroelectricity becomes better in this material because the coercive field reduces as you increase temperature. And you see extremely sharp ferroelectric displacement currents coming up in punt measurements, even at elevated temperatures. Right? You can store the memory state and read it out millions of times at 600 degrees Celsius. You can keep it for hours. Here is the 60-hour data. We have now tested with AFRL for several weeks. That data is not included here. Again, no change in the memory state after weeks at elevated temperature like 600 C. And then if you compare it with any competing technologies out there, there's almost nothing out there. There was one data point out here, this one over here. This is platinum wires, which are made and which are broken and resoldered by passing current at elevated temperatures. They can only last a couple hundred cycles at the very most, right? And they can only store data only for a certain amount of time as well. So really only this ferroelectric memory technology that is the only viable one out there at elevated temperatures. And now with our new data, we have also pushed this up over here. So it becomes pretty much the most dominant technology. I should mention that this can also work at very low temperatures, up to 12 Kelvin. So all the way from 12 Kelvin to 1200 Kelvin, it works out pretty fine. It also works quite well under gamma radiation exposure. This was done with Sandia National Lab. And the last couple of minutes that I had, I want to mention that aluminum scandium nitride is also very well lattice matched or quasi well lattice matched to silicon carbide, because aluminum nitride is extremely well lattice matched. So aluminum scandium nitride is reasonably lattice matched with silicon carbide, so you can grow on it directly. And you can switch capacitive devices, ferroelectric capacitor devices on silicon carbide all the way up to 1000 C, no problem. You'll see as you keep increasing the temperature, the number of cycles they'll switch before they fail starts reducing slightly. But that's not a huge deal, because at elevated temperature, mostly you want reliable read operations than reliable write operations over millions of times. Okay, that brings me to the end, and I want to make a point that if you look at high temperature compute technology, or in general any extreme environment compute, these are sort of the current technologies available at elevated temperatures. 250C silicon, high-T silicon, 300C SOI technology, and 900C NASA's JFET. And if you compare them to the mainstream silicon technology, this is Moore's law line basically. We are stuck in the 2000s or late 90s as compared to the high temperature electronics technology is concerned. That's because thermodynamics takes over at some point, and you can't just arbitrarily scale things and expect it to operate in the same reliable fashion as you get it to do at low temperatures or at room temperatures, right? And so the only way forward, if you want to augment computing at elevated temperatures, is you will have to do memory-enhanced computing. And therefore, having a reliable, non-volatile memory at elevated temperatures becomes very important in this niche but very important area of electronics. So with that, I would like to end and mention that aluminum scandium nitride is a very promising back-end of line compatible ferroelectric material. The resistive ferrodiode memory is quite promising for commercialization. I've already shown you some 2 to 10 kilobyte chips. You can also make very nice 2D FE-FETs with it, or 2D channel FE-FETs. The key scientific challenge is reducing coercive field at small thicknesses, and it's also a very viable candidate for high temperature extreme environment non-volatile memory. With that, I'd like to thank you all again. Thanks Farnaz for inviting, and I'm happy to take any questions.
Thank you. Thanks for a great talk. We have time for a few questions. Any question from the audience?
Thank you. A very impressive talk. I have 2 questions. First one is regarding the scalability and energy consumption. Could you briefly compare the ferroelectric FET and ferroelectric diode, and in which real application, which one is better? And second one is, can we also use LSCAN for capacitor-based memories, or are there any difficulties or challenges behind it? Thank you.
Okay, great. First question is, can you compare these 2 devices in terms of energy? The top one over here and the bottom one. My sense is it depends on the architecture a lot, right? For instance, if you want to think about the first device, a 3-terminal device, if you want to, at a circuit level, it's always going to have more capacitance, more parasitic capacitance because of the capacitive nature of the gate in the transistor. So in terms of reading and in terms of reducing the, in terms of ultimate frequency of operation, that is a limiting factor. This is a simple 2-terminal device. So if you want to compare, again, at a circuit level in terms of read energies and read speeds, this is going to present much lower LCR or parasitic LCR, and therefore the energy consumption is going to be much lower than the above one. Okay, but there are also other challenges. That one is actually much better because it has a semiconductor channel whose on-off ratio can be arbitrarily increased or jacked up. Over here, you're kind of limited by that. I mean, you have to do some engineering to get on-off ratios of 10 to the power 5, 6, and so on. There you get 10 to the 7, 10 to the 8 quite easily, right? And it has a non-destructive read already built in. Even this one has a non-destructive read, but at extremely low voltages, we don't know what's going to happen, right? So there are advantages and disadvantages. The other advantage this one has is very easy to make and fabricate in back end of line. It's just a simple 3-layer structure. That one always involves the semiconductor dielectric interface. One heck of an interface if you ask the semiconductor industry, the hardest one to optimize typically, right? So always more challenging. Yeah. And the second one, can you use aluminum scandium nitride as a simple ferroelectric capacitor? Yes, you can. And like all ferroelectric capacitors, you can certainly use it and then switch it like a ferroelectric capacitor, like I showed over here, right? When you switch it like a ferroelectric capacitor, it's called a PUND, P-U-N-D measurement. Positive up, negative down. When you are switching up, you get this ferroelectric current, and then you again switch up. There is no current because ferroelectric switching has already happened. You switch it down, you get current, then you get no current. So based on this current signal intensity and the direction, you can tell whether memory 0, memory 1. Certainly you can do it, but there's a problem then. How much can you scale it? Because when you scale below a certain dimension, the displacement current is going to scale with the volume of the ferroelectric. At some point, it's going to become comparable to a leakage current, so you cannot really scale it down that much unless you start making 3D capacitors, which is very hard to make, right? The second issue is every time you are trying to read, you are also switching the material, so there is read disturb, or you're writing the material as you're reading it too. So that means the amount of endurance that is available to you is limited. But certainly you can, yeah. Nothing is stopping you from using it as a capacitor memory.
Great. So there's a question online. Can you comment on whether there's an understanding why the material maintains its ferroelectricity at extremely thin thickness and also at high temperatures?
Okay. So I don't have like a quantitative answer to this. Like the qualitative answer to I have is that the woodside structure is the thermodynamically more stable state that this material goes into. And I think if you look at the energetics of the various phases, it seems like the barrier to cross over to the other phase, which is the rock salt phase, is pretty large. Right? So this is the only stable structure it can go into, and there is no other structure it goes into, even at very small thicknesses or at very high temperatures. And so that's, I think, the main reason why it stays ferroelectric, because the polar state, the woodside polar state, is the only state it knows. Now, we don't know what happens at the phase diagram boundary. At around 40% scandium or so, you start getting some evidence of rock salt phase coming in. And so if you are making an aluminum scandium nitride film at, say, 40 or 42%, whether or not it will stay stable in the woodside structure phase at elevated temperatures or very small thickness is unclear. We are trying to do some experiments over them. We're not 100% sure. But this is a good theoretical question to figure out, right? I'm pretty sure the computational material scientists can tell you what is the energy barrier between the rock salt state and the woodside structure at elevated temperature or under a certain amount of strain for very thin films, which is what very thin films experience in this material.
Great, thank you.
Oh, hi, thanks for the nice talk. So you mentioned that the aluminum scandium nitride can be grown like quasi-epitaxially, like silicon carbide. So I'm just curious, how did you engineering that, or have you done any studying to how this like quasi-epitaxy will influence your EC or other parameters?
Okay,
Thanks.
yeah, so the thing I'll mention is we didn't do any special engineering. We just took a silicon carbide wafer out of the box, put it in the reactor, film came out, right? The coercive field on so silicon carbide was n-doped, so coercive field on the negative side did not change at all. On the positive side, the coercive voltage increased because of the depletion region formed in silicon carbide. So you have to be careful how doped is your semiconductor sample, because the depletion layer adds other extra voltage across, or extra region across this voltage drop happens before switching happens. But otherwise, it's comparable to what you do on metal electrodes like platinum. There was one question here, I guess. Yeah.
Do you foresee integration of ferroelectric transistors and the memory, or would you rather other technologies be integrated interconnectedly?
Sorry, can you repeat that?
Would you foresee that ferroelectric transistors and, like, for example, RAM would be integrated directly, or would you rather use silicon for one or the other?
Well, so silicon, I think, will remain as the base layer of compute. I don't think it's going anywhere, right? So the logic layer will remain silicon CMOS. The question is what goes on top of it. And this is where I think ferroelectrics have a very strong chance. Which ferroelectric, again, somewhat debatable. If you ask me, for high temperature extreme environment, we have a clear choice right now, which is aluminum scandium nitride. For leading edge nodes like 45 nanometers and below, Hafnia is doing pretty well, but again, I'm yet to see a commercial product or wide market product that has used Hafnia for its ferroelectricity, not for other properties like enhanced dielectric properties or something like that. So it remains to be seen. Maybe Hafnia makes its way to the market, and eventually over several years, can also improve in terms of switching voltages, that eventually there is a transition over to nitride ferroelectrics. Yeah.
Thank you.
Any other questions?
Thanks for the talk. There have been a lot of recent reports on back-end-of-line compatible FETs and FE FETs made from various amorphous oxide channels. So I was wondering if you could compare 2D and oxide channels for back-end-of-line transistors.
Yeah, it's a great question. I don't have a clear answer to what will win out over there, right? I mean, 2Ds are still pretty nascent. oxide semiconductors have been around for a long time. They are already quite commercial from the display application, right? So there's a lot more research gone into oxide channels for a longer time. The issue with amorphous oxides is that they are amorphous and therefore subject to oxygen movement at the interface, right? And so how much does this present a reliability issue is something that I don't know. 2D chalcogenide, on the other hand, should not have this reliability issue because, again, they are van der Waals, sort of passivated. But how good of a quality can you maintain of 2D materials and uniformity and reliability at the same temperatures of growth as oxides? I think those are the key questions to answer. If the answer to both of those questions is affirmative for the 2D and oxides are like meh, then 2D would likely win out. But that's a big if, again, we don't know.
Excellent. So if there are no more questions here, let's thank the speaker. Thanks a lot for a wonderful talk.
Thank you.